Hello. Um, Let me say hello to Miss Carrillo, if I'm pronouncing that correctly, I hope, and also to Zaid. I wanted to answer your questions. I apologize for taking so long to get this to you. It just needed to sit down and actually get this video done. So let's just get right to it, shall we? Okay, so to answer your questions, let's start with the first. How are intermediate and supermassive black holes formed? So let's say that your intermediate black holes, your everyday black hole, if that's such a term, they're created by being collapsed stars. And then not every star turns into a black hole. These have to be your larger stars or your supergiants. Stars like our sun are not going to turn into a black hole. They're going to turn into red giants and eventually let off their outer shell, and then the inner part of the star will just basically cool off and burn out, turn into a brown dwarf, and turn into this hulk in space. But these larger stars, how they collapse is this. So they have a lot of mass. I mean, these stars are just so massive. Some stars, if you put them where our star is, they extend out all the way to Jupiter. So you can imagine the amount of mass of hydrogen that's in these stars. Well, what keeps a star going is that you have the mass of the gas pulling inward due to gravity. So the gravitational effect of the gas is pulling in. But because of the heat, the incredible heat that's generated because of the nuclear process of a star, that creates forces pushing out. Those are thermal forces. And as long as the forces from the thermal reactions pushing out are equal to the gravitational forces pulling in, then that's called quasi-static equilibrium, and the star stays a nice big ball. Well, when the star uses up its nuclear fuel, it's not going to burn as hot as it used to, which means that the forces pushing out will actually be less than the forces of the gravitational force pulling in. And what the star will start to do is collapse on itself. And when it collapses into a singularity, which is now our black hole. So you have to also understand that people think about size as a black hole, but that size thing is a little bit of a misconception. But we'll get to that in just a moment. So the supermassive black holes are really the fact that a black hole merges with another black hole, and when they merge together, they get bigger. Or they might suck up a nearby star. So supermassive black holes, we believe, are generations of stars that have turned into black holes that have merged together, or that really big black hole sucked in another star, and now it took its material and became part of the black hole. So supermassive black holes just don't go from a supermassive star to a black hole. It's the culmination of a lot of black holes merging together, or black holes sucking in more stars and giant gas clouds to increase their mass to make them supermassive. Can black holes collapse? Well, not really, because in actuality, the black hole is the collapsed star. So once you have a black hole and it's collapsed into a singularity, there's nothing for it to collapse into. It is now broken down into the smallest thing that it could possibly be, which is the singularity. Pardon me. Keep looking at the dust on my glasses, and it's driving me crazy. Or should I say the fog on my glasses? So let me clean that off. Okay. Sorry about that. Let's continue. So let's see. We've done how small is a singularity? You know what? To talk about singularity in terms of size, it's hard to do that because when you get past the event horizon of a black hole, the laws of physics break down. The laws of time and space break down. So we can't really think about it in this three-dimensional space that we're used to. It doesn't have that kind of dimensional size. What we can say is that it has a lot of mass. And so that mass is a lot. So mass is, we think of it in terms of magnitude or size. The singularity is this infinitesimally small point. So smaller than an atom, it's like all this mass broken down into a space that is just, when we say infinitesimally small, we're like so small that we can't even imagine how small it is. It's just this one solid single thing. There's not a space in between the particles of the atom. It's just a singularity. It is a thing. It is just an infinitesimally small thing. I know that sounds crazy. Best I can do. Okay. Um, how fast do we need to escape a black hole before we go over the horizon? That really depends on the size of the black hole. But the speed of light is always a good speed to be talking about. Um, so how fast depends on the, because remember what you are doing is you're taking the gravitational force and you're trying to create, you need to be going at a speed where your speed overcomes the gravitational pull of that black hole. So it's kind of hard to say how fast that is. But light traveling by a black hole might get bent towards it, but it's still traveling so fast that it doesn't get sucked in, so it keeps going on its way. Which is actually the effect that Einstein predicted called lensing. And it's the way that if light comes from behind a black hole towards you, and it has to pass that black hole, it will actually start to distort because of the fact that the gravitational pull is changing its trajectory. So when you see these pictures, it creates these kind of like crescent type light images, and that's called lensing. Let's see. How fast do we need to do to escape? We did that. How many Earths could fit inside a supermassive black hole? Well, now we have to kind of get out of the misconception of what a black hole is. The black hole is the singularity at the center of the event horizon. The event horizon isn't actually the black hole per se. It's a region of which once you pass it, it's a distance. And that distance is, once you passed it, you can no longer escape. And that's also where these laws of physics break down. So you can't really fit an Earth in a black hole. It becomes part of the black hole. How many Earths can fit within the event horizon of the black hole? Well, that's a little bit of a hard thing to answer too, because if the Earth went into it, first off, it couldn't go inside of it as a whole. The gravitational forces are so great that the Earth would break up into dust, and it would just suck the dust in. But theoretically, if you could put the Earth in the event horizon, and it didn't lose its shape, billions of Earths could fit inside of it. And I'll get to that in a moment when we talk about a later question that you asked. Is there a limited amount of mass in a singularity? No, it's really infinite, because as much mass that you can suck into the black hole is as much mass that you can have going in. At least that's how I understand it. So black hole comes, sucks up a big super giant star, sucks in another and another. It just gets more and more massive. And then when we get to that other question, which I'll get to, you'll understand how much big it can get. What really happens in a singularity? We don't really know. We have some theories because, like I said, our way of describing the laws of physics break down. But essentially what happens is all of this mass gets crammed into an infinitesimally small point. There are no more particle, like space in between the atoms and the particles. It's just one solid hunk of mass, and it's infinitesimally small. So what happens in the singularity is that all that mass gets crammed into, it's like your fist. Grab it, it's tight as you can, and you pretend that there's no space anywhere. Now, break that down millions of times. And to give you a sense of scale, this infinitesimally small is small. To the point where let's look at it like this. If the sun were the size of a white blood cell, the Milky Way galaxy would be the size of the United States. Think of that relative comparison. Now, you take that sun and you squash it down to a singularity, it would be millions of times smaller than that grain of sand. Does that make sense? Good. How much more gravity does a black hole have than Earth? Well, a black hole could have the exact same gravitational pull as Earth if you think of, let's say you have the Earth, two Earths, and there was a moon orbiting both of them. One of them collapses into a black hole. Well, the mass is conserved. You don't get more mass. So when this thing turns into a black hole, the moon would just orbit the black hole normally. So when you say how much more gravity does the black hole have, it has the same amount of gravity. But that gravitational pull in its immediate region increases as you take that mass and condense it into a smaller radius. So unlike on the Earth's surface where you have the gravitational pull of the Earth, at the black hole surface, if you condensed Earth into the size of a black hole, then that immediate region, the gravity goes up millions of times. Millions of times. Let's see. An example is if the sun turned into a black hole right now, not that it would, the Earth would orbit it just like nothing happened. Because again, the mass is conserved. It's near the black hole that the gravitational pull gets extremely great. Let's see. Are there other types of black holes other than mini-stellar, intermediate, and supermassive, and what are they? Well, this is how I'd break them down. You have your normal-sized black holes, which are stars that died. You have microscopic black holes, which you could get from like taking particles and colliding them together in a particle accelerator. And then you have supermassive black holes, which is the combination of black holes colliding together and sucking in more black holes or other stars. Let's see here. Does all of the gas and dust in an accretion disk get sucked in? Eventually, yes, it does. Why? Well, remember, what's happening is when you have an accretion disk, the particles that are moving around the black hole have centripetal force, or force due to it going around. And then you have the gravitational force pulling in. Well, in a perfect orbit, like when a satellite orbits the Earth or the moon orbits the Earth, what you have is that the gravitational force is equal to the centripetal force. But when you have a black hole in the accretion disk, the gravitational force is slightly greater than the centripetal force. So since it's slightly greater, the particle is still going around. It still has force resisting, but it's less than the force pulling. So it's a spiral effect. So eventually it spirals in with a tighter and tighter radius until it gets to the event horizon and gets sucked into the star. Can things weigh faster than light escape a black hole? Well, there are only some theoretically few things that are faster than light, but as it stands, if it goes past the event horizon, it just isn't getting out. But Stephen Hawking theorizes that black holes have this thing called Hawking's radiation, and that means that they would actually radiate their mass out, and black holes could eventually evaporate. Now, not every physicist believes this. There's a lot of problems with this theory that have yet to get sorted out. But theoretically, that mass could radiate out that Hawking theorizes, and it would eventually, so essentially like water in a glass, it would just evaporate into nothing. Theory, not proven by any means. Let's see. If there was an entire black hole smaller than an atom, what would its mass be compared to? Well, all black holes are smaller than an atom, and its mass we compare to what's called solar masses. So when our standard is the mass of the sun, and anything beyond that would be like, let's say it was twice as big as the sun, so we'd say, oh, that star is 2 solar masses, or that black hole is 3 solar masses. So we compare it to the mass of the sun, and those masses could be humongously big. Get to that in just a second. That's my professional term, humongous. Or ginormous, more like it. If there was an entire black hole, okay, we covered that. Was there ever a black hole that could destroy a galaxy? Well, theoretically, yeah. If you had the black hole and it could travel around sucking up stars as it goes and eventually get all of them, true. But that's not really how they work. In fact, we believe that black holes are necessary in the formation of galaxies. So they're a vital part of galaxy formation. So I wouldn't think of them so much as could a black hole destroy a galaxy, but more so that a black hole is part of a galaxy existing. Now, I will say this. There is an effect called beaming, where the particles that are spinning around the black hole, the accretion disk, if you will, those particles get so energized that they get really, really hot. Well, when things get really, really hot, they don't emit light, they emit X-rays. So you get these giant jets coming out of the black hole, and I drew a little sketch of one here, and it's like the black hole's at the center, and you have these jets going out from its pole. So there is this one rare galaxy that is destroying another galaxy because its jets are actually blasting another galaxy with X-rays or gamma rays, I believe. And so anything that's in that galaxy is being destroyed. Look up, I think that you could Google it and look for images of Death Star galaxy. And it was just unfortunate that this one galaxy that was beaming happened by another galaxy, and it got caught in that beam. Now let's say that this is the Milky Way galaxy, and we passed by that beam. There'd be nothing we could do, because these rays are literally blasting the entire galaxy. So it's not that the black hole goes around sucking up stars and destroying a galaxy, but if a supermassive black hole is emitting these jets and another galaxy passes by those jets, it could blast away that galaxy. Let's see here. Let's see, was there ever a black hole that could destroy a galaxy? Yeah, so we did that. What is the biggest black hole ever discovered? So the largest black hole that I find that we've discovered is OJ 287. It's 1.8 billion solar masses, which means that's 1.8 billion with a B times the mass of the sun. And this black hole is about 3.5 billion light years from us, so you don't have to worry about it coming over and sucking up everything and then like eating your dinner. No, it's a long way away. Now the radius of this black hole, and again, let's not deal with the misconception. The black hole is infinitesimally small, but the radius of its singularity to the event horizon, that radius is actually 65 billion miles away. So to put that into perspective, Pluto is only 3.6 billion miles from the sun. So basically, our solar system could fit well inside the event horizon of this black hole. I did a little quick calculation that would say that the black hole, the event horizon of the black hole, is 18 times greater than the radius of Pluto. Wow. Okay. Why should people learn about black holes? They're fascinating. The idea that there's this thing that could suck up anything, and time and space as we know it gets distorted into this thing that we can't even conceive visually or sometimes conceptually is very fascinating. And for some odd reason, we as humans are just fascinated with the idea of there's something out there. Once you go into it, we have no idea what it is, what happens. There's some that think that for every black hole, there's a white hole. All the material that gets sucked in, there's a white hole somewhere in the universe where the energy or the mass is being spewed out. It's just the possibilities are endless. Which brings to your next question is, why did I want to study black holes? Because people find them exciting. And I love to talk about them, because if that's what I can use to get people's interest in science, then that's the thing that I think is universal. I don't care where I've gone in the United States. If I bring up black holes, there are kids out there and adults that want to talk about it and the possibilities of what exists with a black hole. So I wanted to study them because they're fascinating, not only to me, but they're kind of universally fascinating to everybody that I run into. I might talk about the stars, and they'll be like, oh yeah, stars. Some people into it, some people not. Or planets. Some people get it, some people don't. Black holes, now people's eyebrows raise. Oh man, black holes. Is it true you can get sucked into a black hole? Is time travel possible? It fascinates people. Let's see. What do I do for my job? My official title is Director of Physics Laboratories. I am in charge of all the education laboratories of the physics department. I teach experiments in physics 1 and 2, and I teach the recitation classes, or physics problem solving classes. I'm also head of the rocket team, where we compete in a NASA competition each year called SLI, or the Student Launch Initiative. That's where we design, build, and launch a rocket to take a scientific payload up to an altitude of 1 mile. So there are a lot of aspects to my job, and I also go to public schools and talk to students like you to get them excited about science. We sponsor at our school 2 science clubs. One at Rose Park Magnet Middle School, and another at McKissick Middle School. Your final question is, what is the best part of my job? I love it when students get it. You're sitting in the class and you're looking at the board like, what? Not getting it. And then, you get it. You start to explain it in a different way and present it and kind of bring them into the problem and boost their confidence that that they're smart enough to understand it. And then they go, that's how that works. I finally get it. that moment I live for. I love it the moment. And it doesn't matter if it's a young someone in middle school or they're an adult learner in college or beyond that. I just love that moment when they have something that they didn't understand and they began to understand it, and I was a part of that process. What are the most challenging aspects of my job? Well, one, time management. There's so many things that I enjoy doing that I sometimes, you can get caught in trying to do too much. And that's one thing that I'll point out that, you know, there's a lot of things that are fun. You might want to be on the chess team or the key club in high school. I don't know if your area has those. But you might want to do all these different things, but you have to manage your time so that you can do them, and you don't want to take on too much. So the hardest aspect of my job is to maintain and manage my time so that I get everything done. I rather do a few things really well than a lot of things average. You know what I mean? So that comes to the end of the questions. I know I took a while to do this, but I know you got to wrap this assignment up. So if you have any questions about anything that I've said, feel free, shoot me an email. I will get it back to you ASAP. I'll jot you a quick answer. And I'll also provide some links in the show notes below. So thank you very much, and I hope this has been beneficial to you. And if you ever have any other questions, feel free to let me know. Take care. Bye-bye.